Hi, my name is Pin Nu. I'm a postdoc at the University of Oxford. Today, I'm going to talk about modeling cardiac motion via spatial-temporal graph convolutional networks to boost the diagnosis of heart conditions. Why do I look like graph convolutional networks for cardiac motion estimation? There are the reasons. GCN produces useful feature represented nodes in networks. There can be arbitrary node position in an image. We can use GCN to explore and enrich information with cardiac structure graphs. Recently, there are some GCN-related applications in medical image analysis, such as disease classification, image segmentation, and landmark detection. In our knowledge, we are the first to model cardiac motion with a geometric deep learning-based architecture. In this work, we construct a cardiac structure graph from the mid-ventricular short axis view. According to the AHA 17 segment model, there are 6 segments in the middle slides. To be clear for the number of segments, I would like to show you the segment model based on 3 sections of the left ventricle: base, mid-cavity, and apex. We rotated the initial lines around the barocentre nodes of the left ventricle by every 15 degrees. The intersection nodes of the rotated lines and the endocardia and epicardia borders are chosen. The barocentres of the left ventricle and the 24 node locations from both the endocardia and the epicardia are considered as cardiac structure graphs. We construct 2 undirect spatial-temporal graphs on the cardiac structure. One graph features both intra-endocardial and inter-frame connection. The other graphs includes both intra-epicardial and inter-frame connection. In both graphs, the inter-frame edges connect the same nodes between consecutive sampling frames. Node locations, 2D pixel coordinates xy, are defined as input to the spatial-temporal graph convolutional network. The cardiac motion sequence is given as input to the STDCM encoder decoder framework. 3 slides input predicts future cardiac motion in 1 slide. There are our sampling frames over the whole cardiac cycle. The sampling rate is 3. If we use frame 036, the model will predict cardiac motion in frame 9. Also, frame 369 will be used to predict cardiac motion in frame 12. The output of the encoder and the period motion are fitted into the decoder. The sum of the output of the decoder and the period status represents the output future cardiac motion, which is used in the left ventricular function evaluation. There are 9 layers of STDCM blocks in the encoder and 5 layers of STDCM blocks in the decoder. Let us zoom in on STDCM block. It includes a spatial graph convolution and then a temporal convolution, which extracts spatial and temporal features respectively. The important element of STDCM is the spatial graph convolution operation, which provides a weighted average of neighboring features for each node. A 1D temporal convolution is used along the time axis, which extracts the temporal feature of each node independently. The data we use is from the UK Biobank. We focus on the mid-ventricular short axis review. Each sequence contains 50 consecutive time frames per cardiac cycle. The sampling rate is 3. We compare 3 cardiac structure graphs and measured the predicted node location with the ground truth using the mean square error. Graph nodes from the epicardium have the least MSE and achieves better predicted performance. Here, one pixel size is 1.8 millimeters. Here is a comparison of cardiac motion estimation between the proposed methods with cardiac structure graphs constructed from the endocardium and the epicardium, and a graph constructed from both the endocardium and epicardium. Both methods better predict the location of the epicardium nodes than the endocardium nodes. The node location are predicted very accurately on the epicardium by both methods, especially the 36th and 45th frame. Here is an example of a time series of endocardium's reduced thickness and reduced strain in the 6 segments of myocardia from the prediction and the ground truth of node location of a healthy volunteering. Experiments shows that the proposed methods performed well in estimated endocardial radii and characterizing cardiac motion features from regional left ventricle analysis. In conclusion, we propose a spatial temporal graph convolutional network to characterize cardiac motion. We also evaluated and compared the effect of different cardiac structure graphs on cardiac motion estimation. The model learns meaningful spatial temporal patterns of the cardiac motion that can be used for left ventricle regional function analysis. The model has been applied to explain motion characteristic features between prediction and the ground truth. That's all. Thank you so much for your attention.